Hey, hello everyone. Good morning and good evening. My name is Ramesh Ponnada and welcome to Ramesh Tech Solutions. Today I am very happy to discuss a very important topic in power integrity analysis. So, while we are designing any PCB or package design, it's very important that we perform this power distribution analysis so that we have a proper product. So to introduce myself, my name is Ramesh Ponnada. I am an signal integrity, power integrity and tool development and automation expert. I have been working in this industry from last 17 years. So in this topic, we discuss about a very common practice of power distribution network on a PCB and package, and I want to talk about the key foundation of a power integrity, which is DC drop analysis, and how it plays a important role in all our modern electronic designs. Okay, so now what is DC drop? So many people think that power is just a voltage number, right? Like if we are in a household in India, we have 240, in US it is 120 volts. But if you are talking about the electronic devices like mobile phone or the laptops what we are using, these operate at a very low voltage, a direct current voltage, and the current generation mobiles operate at a 1 volt, sometimes even a 0.8 volts. And as these voltages reduce, the value reduce here, it becomes very difficult to maintain that precision and deliver the same voltage from source to the receiver. So when I say source here, I meant VRM. VRM means voltage regulator module, and then this voltage from the voltage regulator module starts from this component, travel through the PCB and then reach our IC, the main component which do all these functionalities. So whenever the power flow from one device to other device through a medium called printed circuit board, because this printed circuit board will have a structure, a metal structure which contains copper. So whenever some current flows on this metal structure, there will be some amount of loss in that voltage. In this example, let us say we have 1.5 volts here, at a VRM, and then the power is traveling to the PCB, and then what happens is, because of this resistivity, every copper will have some resistivity, and some current flows through this resistance, some amount of voltage drop will be there. From the equation, voltage is equal to current into resistance. So now here, let us say some 1 amp of current is traveling from this path, because the IC need 1 amp of current to operate, and because of this resistance offered by this rail here, by this copper shape, and let us say the resistivity, every material, every structure will have some resistance, and let us say the value of resistance is in ohms, and we have 20 milliohms as a resistance for this structure, and because of it we are going to have 20 milliohms into 1 amp, which is contributing, it's like 20 millivolts drop. So whenever we have 1.5 volts, we are going to have a 20 millivolts of drop, and it will become, you can understand that it's going to be like 1.48 volts, like that. Sometimes even the voltage drop will be even more, right? Because of if you have more current traveling and the resistance is more, then you may even fall into category of 1.45 volts, which is dangerous, and this will make the IC chip to behave unexpectedly. Alright, going to next slide. So why it's very important, why should we understand all these things like the voltage drop, VRM, the transmitter to the receiver, which is SOC or DRAM. The main necessity here is whenever we are kind of trying to perform some task with the IC here, it is very important that this IC is getting enough voltage to keep it operating. Let us say this IC is manufactured to operate at 1 volt. It requires 1 volt. If we are not able to deliver for some reasons, the supply going from VRM to IC, because of some reasons, it is not able to meet this requirement of 1 volt, then this IC is going to cause several issues, something like instability, timing failures, and sometimes the design may not work as expected. So many of the engineers will try to address this issue in the so early of the design, instead of performing some design and then taking it to manufacturing and then facing the issues. It's very important to address this during the development stage only. Okay, so that's why it's very important. So as I try to mention a quote here, voltage at the IC pin, whatever we are seeing at the IC pin, is not equal to VRM. The VRM is voltage regulator module, which is a transmitter which will pump the voltage from here, and let us say we have here 1.0 volts. The moment the current travels through this path and reach here, because of this geometry and various other factors, this voltage may reduce to 0.98 volts, and if it even reduces further, like it can be even 0.9 volts because of some very narrow traces or more stitching or less stitching vias. This could even reduce to 0.9, and that will cause this IC to fail. It will not work as expected. Then we may going to see a timing issues, like we don't have a proper setup time, hold time violations. How to avoid it? So to avoid these issues, it's very important to perform a DC drop analysis using some very well-known EDA tools in the market. Some of the tools are like, if we start the major vendors in the market, we have Cadence, we have Ansys, we have Siemens Mentor tools who can help us to perform this analysis even during the development stage. So whenever we are kind of checking for a DC drop analysis, it's very important to identify what is causing this issue. So in this case, let us say that we have a VRM. VRM is voltage regulator module. Usually that component is called PMIC. So the PMIC components generate the supply, the DC supply to this ICs. So what happens is, let us say this PMIC is operating at let us say 2.5 volts. 2.5 volt operating PMIC at 2.5 volts is happening on some high-end computing machines, but if you are talking about your laptops and mobiles, those may be operating in 1 volt or 1.5 volts. The voltage levels are reducing as the technology is enhancing. So now here, whenever we have a supply of 2.5 volts here, and this IC demand like a 3 amperes of current to operate all its functions. So what we are going to do here is, the current travels from here, the 3.8 amperes current travels from here, but because that routing of the trace is very narrow, that's why when we perform the simulation with this setup like 2.5 volts at PMIC and 3 amperes current consumption at IC, which is a sink, then we are seeing the supply is going through this way, and the moment it reaches the IC, this 2.5 volts will become like a 2.2 volts because of the drop. So if you look at the legend scale here, the legend scale is 2.5 volts in the red color, the green is 2.4 volts, and this blue is 2.3, and this navy color is 2.2 volts. So we are almost having how much? 0.3 volts of drop because of this narrow line. Now how can we improve this? one good way is try to increase this trace width, like more wider traces, so that we will let the current to travel freely here, and also this will help you to have a decrease in the resistance. So as we look at the equation V is equal to IR, we don't have a control on I because that is what it is demanded by the IC, a 3 amperes of current. But the resistance, we have a control on the resistance because we have some space available here, so you can increase the width of these traces so that the resistance will be decreasing. So once the resistance is decreasing, which is directly proportional, even the voltage drop will decrease. So in this category, in this way, if you are kind of widening these traces a little bit further, okay, like this, or you try to have a shape like this, a copper shape like this, then we are going to experience a very good improvement in the voltage reaching to the IC. So maybe now this may become like 2.5 volts. The moment the voltage reach here, it may be like 2.4 volts. The IC might see 2.5 volts, which is still we have a drop, but it's within the specs of the IC. So this is one of the ways we can improve the DC drop performance of a design, you know. So though I'm giving example on a PCB, but this is applicable for package also. Now, as I mentioned earlier, it's very common practice that people ignore this analysis in a development stage. They just take this design to the manufacturing. Once that PCB got fabricated and they are doing this board bring up activities, they see the DC drop or the voltage drop issues, and they don't see the IC is not functioning well because we have a huge drop in the path. At that time, they come with a lot of problems, like they do some stuff on the PCB which is not very easy and very time consuming, and sometimes it's also cause other sections of the design to fail. In this case, just for sake of improving the flow of current, they may kind of do some jumper connectivity from here to here, because the path from here to here on the PCB trace, let us say that there is some PCB trace like this, and it is narrow because it doesn't get a proper current till here with a trace of let us say some 5 mils. Okay, then what they do is they're gonna come with a wire later which is having like a 20 mils diameter. Okay, and then it is gonna carry this current. So these are some kind of post fabrication solutions people try, but if you have taken care this one during the design stage, you don't have to do all these things in the post fabrication stage. This will improve your product launch time and reduce your cost, and moreover doing this kind of stuff will cost lot of engineers time and efforts. So this is what we could be avoided. And now I just gave example of a mobile phones or laptops, but imagine that you are or your company is working for a products at a data centers or whatever the AI and ML applications we are using. They are operating a huge servers which are going to consume not just 100, it is going to consume even 300 amps of current, 400 amps of current, and at that consumption even a voltage drop of 10% could cause the design to fail. And whenever we have this kind of failures on this kind of designs, it's not just a drop analysis, it's not just a voltage drop problem that will affect the signal integrity and power integrity of the design. So when you don't have a proper voltage reaching the IC, you can't expect the IC to function properly, and it is going to cause a delay in its response. Let us say you expect let us take a simple analogy of a kind of a motor, okay, a rotor which is rotating with a shaft like this, and here you are having a pipe and you are just throwing water towards it. and if you have a very high pressure water flowing through this motor will keep rotating because of the pressure you are creating. But let us say your pipe has some holes here, some holes, then water will be leaking the other side, the pressure will decrease, and this rotating instrument will reduce its speed because the pressure has been reduced. In the similar way, whenever you don't have enough voltage supplied to the IC, even the IC performance will be decreased because some amount of voltage drop has happened in your PCB and it is not reaching the IC. So this is one of the simple analogy I want to explain. So to conclude, whenever we have a designs which are very high performance and compute intensive, it's very important to do this DC drop analysis in the early development stage. And this approach will help your team, not only your team but also your company, to save a lot of cost in the board respins, and it will improve the design quality, and it will make your product launch on time to the market. So as I mentioned, some of the risks how you can reduce with the DC drop analysis, how you can save the cost, and make sure that this power integrity is ensured so that the other sections of the design like signal quality or timing related issues could also be minimized by taking care of this issue on the designs. And I just try to list out very widely used EDA tools in the market which are very popular. And in my case, apart from these simulations, I spend a good amount of time in performing these automations. I work for a company, a semiconductor IC company, which will design this kind of products in some several thousand volumes, and for every design we need to do this repeated analysis every day. So I have developed some automation scripts so that users has to not spend this much time, and the automation will take care of running the simulations and giving a report whether this voltage rail on this design has been successful or failed, and accordingly a report will be generated, and then this could be used, this report could be used between the layout engineers and simulation engineers, and accordingly they can improve the power distribution network quality. So if you want to hear more on this kind of topics, and you want to understand how this automation help in detail, or you want to know how to perform these simulations using the EDA tools I mentioned like Mentor, Hyperlinks, Ansys SIwave or Cadence PowerDC, please let me know in comments so that I could try to work on them and share for you. Thank you so much. Hope you enjoyed the session.